Okay, welcome. So tonight I'm going to talk a little bit about blood flow and pressure and what things you need to really understand a little bit in order to do well on the exam. And unfortunately, it's going to be a little math, a little physics, but we're going to get through it together. I have the whiteboard out. I will forewarn you that it's a little delayed, and so my handwriting's pretty poor on the whiteboard, but I have a hard time getting some of these equations to come up nicely. They get very pixelated when I try to bring them in from saving them. So I just want to talk first of all about a couple of equations that you need to understand and know very well. Some of these may be from the last module. They do relate still in this module, so we're just going to go over them. And the first one, of course, is cardiac output. Cardiac output is the heart rate times the stroke volume. Due to the high volume that we typically see this in, it's usually expressed as liters per minute. And in a normal, healthy, average human being, males are a little bit more than females, but we would see anywhere from probably 4.6 to about 5.3 liters per minute in a normal cardiac output at rest without a lot of activity. As you know, and I think it's important that as you learn about these equations and learn how to do calculations, not that you have to do calculations on the exam itself, but you have to have a general idea of what's normal and how things can be influenced. Heart rate is in beats per minute, and stroke volume is in milliliters, so there is a conversion there from milliliters to liter per beat. Now, stroke volume, we're typically talking about the left ventricle and how much blood comes out during that ejection fraction. If you remember that phase of the cardiac cycle, there's blood the pressure builds from the isovolumetric contraction in the left and right ventricles, but we really just focus on the left when we're talking about numbers and so forth. And then when the pressure is finally so much, it opens up the semilunar vessel, and then the blood comes out into the aorta and into the pulmonary arteries, and then the valves shut, which is the second heart sound. That is called a stroke volume. Now, we don't really mention this a whole lot, but just as a little side note, ejection fraction is how much of the blood, oh, that's really bad. Let's just erase that, shall we? Let's just erase that. Ejection fraction is the amount of the stroke volume over the total volume. So it's a fraction. Sometimes it's converted into a percent. And once again, we're talking about the left. The right has a slightly less because it's smaller, partly, and partly it has less pressure because it's going closer. But the ejection fraction is usually about the same. And what we see in a normal, average resting person, ejection fraction is probably about 0.75 or 0.78. So you still see blood in other words, the ventricles don't fully empty when we're contracting and pushing blood out. And that's good to know because we sometimes need additional blood, or we need additional nutrients to the cells, and we need it a little faster, and we can do that. We can affect the heart rate, certainly. We can affect the heart rate there, and we can affect stroke volume. So we can actually affect how much blood comes out per beat. And part of that, as we talked about in the last one, was that calcium. The longer the plateau, the stronger the strength of contraction. In other words, the higher the stroke volume. In addition, with exposure to epinephrine and norepinephrine, which you should have learned about in 264 when you talked about the autonomic nervous system, they'll also increase the heart rate. So you can get this cardiac output, which is normally, let's just say for a real generic value, about 5 liters per minute. You can get it almost 5 times that amount during heavy exercise and during hormonal stimulation, like if you're running through the forest for your life type of thing. You can actually get that quite a bit, and that's important because your muscles are going to need the oxygen and other nutrients that are coming from the blood in order to save yourself from the bears. So just know that this first equation here is one that you do need to know for your exam. Oops, my star is not working very well. This first equation, the cardiac output equals heart rate times stroke volume, and once again we usually express that as liters per minute. Now I think there is a hello. There was at some point an eraser. I do not find it now. So maybe we'll just stop sharing the whiteboard and see if we can share a new whiteboard. It might come back with the same stuff. Oh, it didn't. Yay. Okay. So another one that you need to understand, and this is part of blood flow and regulation, so it'll seem a little bit more familiar as far as, oh yeah, we just read that. And that is, oh, that does not work. Let's go back to the marker. I thought I would use pencil, and that did not prove to be a good thing. So is what we call MAP, mean arterial pressure. And this is equal to your cardiac output times your peripheral resistance, your PR. This is another equation that's important to understand. So we all know what cardiac output is now, so what is peripheral resistance? Well, peripheral resistance is this idea that you have resistance to blood flow. Resistance is the opposition to flow. Peripheral resistance is talking about all the factors around the vessels that cause overall that force that opposes flow. So your mean arterial pressure is going to be your cardiac output, so what's coming out, and then when you factor in resistance, what is the force opposing that flow? And that ends up being the mean arterial pressure that we're talking about. Now, the reason that this is important is it leads further to a concept that we're going to talk about in what's called Poiseuille's law. And I probably said that wrong. I don't speak French at all, and so it's so different from Spanish. So I probably said it wrong, but it's Poiseuille, Poiseuille's is how I've always learned it, law. And this is a very important equation for you to know, and especially for your exam. And your notes give you lots of different, derivations of how that comes about. And it does have to do with peripheral resistance and that force that opposes flow. But ultimately, what it really comes down to, and that's why I didn't want to necessarily bring up all those things, is it's essentially telling you that small changes in radius or in diameter make big changes in flow, in the resistance. And so if we look at, and we're actually going to look at, I'll still share this, even though, like I said, I don't know if that's not that one, so just a sec. This is where we typically try to explain it. And let me get out my, very, very pixelated. But peripheral resistance is equal to a constant times the vessel length over pi over radius to the fourth power. So if this radius changes, say, from 2 to 4, 2 to the fourth power is 8, 4 to the fourth power, hang on just for a second, 64 times 4 is like 128 or something, or more than that, sorry, 256. And so you can see that your peripheral resistance changes dramatically when the radius gets bigger. The peripheral resistance goes down dramatically. If we went from a 2, though, down to a 1, you're looking at a huge factor of how that peripheral resistance will increase. So the smaller the radius, the higher the peripheral resistance is what we're really saying with this. And then combined with what we talked about a little bit with flow and with peripheral resistance, cardiac output, we see this final document here, or equation. Our flow rate is dependent. Pi, as you know, is a constant. Oops. Pi, as you know, is is a constant. So the change in pressure from the vessel, from the beginning to the end, times the radius over, and I think actually V is viscosity. I might have said vessel length, and I forgot to mention the viscosity as well. And so another constant. And the length, in all purposes, we kind of consider the length kind of a constant too. And so you can see that, once again, the flow rate will change based on the radius. So once again, Poiseuille's law essentially says that if you increase the radius, so if you do a vasodilation, you're going to see larger flow. If you do a vasoconstriction, you're going to see a dramatic drop in flow. And this is important for us to understand because it's basic physics and fluid dynamics in the sense that our bodies, we can control that radius due to some local regulation and some long-term regulation as well, which we're going to talk about, some hormones that can help with that. And so we can actually help control the flow rate in our bodies based on the constriction or the dilation of the blood vessels. And that constriction and dilation of the blood vessels will also lead to what we call our blood pressure. Now, most of you should have gone over this already, but just as a brief recap, let's look at, if I can find it really quickly in my thing. All right. So let's look at this. Just a second while it's uploading. It's uploading really slowly, so let me try that again. We'll actually try the other one that's here. It's just the JPEG. Okay. So this is showing you pulse pressure, but it also shows you what we see pressure in arteries versus arterioles versus capillaries versus veins. And so this is a good diagram to kind of discuss some of this stuff. So you can see that our highest pressure is typically in the aorta, which reflects the pressure in the left ventricle. And I know some of you had questions about that. When we talk about blood pressure, we're really trying to find out ultimately what the pressure is at the aorta, which gives us a good indication of what's in the heart. Now, of course, we can't go in always and measure pressure right at the aorta, so we use our upper arms. It's closer to the aorta. It gives us a better feel. So if it's high there, it's going to be higher, even higher at the aorta. As you can see, arteries are slightly less. We have a slight increase here, aorta. Arteries, arterioles, we start going down. Now, you may be asking yourself, well, certainly an arteriole has a lower diameter or a smaller radius than the aorta, so technically, Sister Foster just taught us that that should be a higher resistance, a higher force that opposes flow, and that is true. But there's only one aorta, and there are hundreds of arterioles. So overall, our overall peripheral resistance we actually see starts to drop. And then, as you know, at the capillaries, it's fairly low, and at the veins, it's negligible. So here's another example with systolic pressure, where at the highest point of contraction, where all that blood's coming through, and then the lower pressure, where the vessel's completely at rest and the valve is closed and there's no blood going through, that's diastolic, or pressure at rest. And so the mean arterial pressure is a portion of that. It's not quite half. A lot of students think it is, but it's not quite. It actually is the difference between the systolic and the diastolic, but we talk about it using this formula where we take a third of the difference plus the diastolic pressure, and that gives us a more accurate mean arterial pressure. Anyway, so you can see that pressure in the vessels, because of the number, if we had more than one aorta, this would probably be lower, but we see the pressure goes down and is pretty negligible at the veins. And so what we're going to see is our ability to influence pressure in order to influence flow is going to come here, mainly in the arteries and in the aorta. We don't see a whole lot in arterioles, but we mainly see it here in the arteries and some of those larger and medium arteries. And as I mentioned, we're going to talk about that as regulation. So, and hormones aren't the only, we have various types of regulation. We have baroreceptors, we have just, the idea, for instance, of exercise itself will increase cardiac output. Like I said, if you're running around, there are some hormonal influences there, but also just the mechanisms of exercise where the muscles are propelling the blood towards the heart. The heart's going to fill more, so the heart's going to empty more. Starling's law, which we haven't really discussed yet, Starling's law is essentially what goes in comes out. So if you put more blood into the heart at any given time interval, you're going to get more blood out of the heart. Once again, that's that idea that ejection fraction, you're going to get a portion of that out each time. Now that ejection fraction can also increase, as I mentioned, but in the meantime, you can also do it by increasing blood movement. And you know that our skeletal muscles help compress the veins, which helps propel the blood. When you're lying down versus standing up, you have less of the effect of gravity, and so you'll have a slightly higher increase or a slight increase of venous return, and so you'll see a slight increase of arterial output in that sense, or blood coming out of the arteries. So we do regulate blood pressure in a couple different ways. We do it short term, like I said, a baroreflex, which is measuring pressure, the chemoreceptor reflex. We will talk about the adrenal medulla, which contains epinephrine and norepinephrine, and the central nervous system. And so let's take a look at the summary diagram that we shared with you in the reading material. If I can find it here. Not all of them transferred over. And that one does not look like it did. So I'm going to go ahead and pause and pull it down, and we will get right back with you. Hang on just for a sec. Okay, and we're back. The beauty of Adobe Connect sessions instead of Gene Screencasts, which have a harder time pausing and getting back into it. So this is the diagram that we shared with you. And as you can see, it gives us some of the short-term mechanisms that we see. The first one that I mentioned, well, both actually baroreceptors, which are stretch receptors. The higher the pressure, the more the vessel will stretch, and that stretch receptor will then send signals in order to show, in order to let the brain know that that we're having higher pressure, and that we need to change that regulation, or change it so that they actually will respond fairly quickly, so that you can get sensory neurons to say, okay, we need to either slow down the heart or do something to decrease that pressure. And the opposite is also true. If the baroreceptors aren't firing very much, if they're slightly lower blood pressure, then they will send signals back to cause constriction and cause an increase of blood flow, or of pressure based on flow. So we also have chemoreceptors. We'll talk more about this in respiration. But if the oxygen content is low, which isn't as sensitive actually as a high CO2 content in the blood, that will also trigger receptors for increased blood flow to try to get the CO2 out faster and to get the oxygen in faster where it should be. We also see that there is sympathetic and parasympathetic nervous system regulation. So sympathetic will help increase, this will cause increase of vasoconstriction in certain vessels and vasodilation in others. In other words, which is, I know, hard to understand, well, unless you had recently the autonomic nervous system. However, we increase the constriction to increase pressure, but we also do a vasodilation in certain ones to get more blood, for instance, to the skeletal muscles. And so you see that both parasympathetic input and sympathetic input influence not just the heart rate, but it will influence the pressure as well. So if you have parasympathetic input to the heart, that lowers the heart rate. And as you know, more blood will come in, therefore more blood will go out. With sympathetic, you see an increase in heart rate, but you also see an increase of strength of contraction. And so because of that, even though it may seem counterproductive, you actually end up getting more blood out because of that sympathetic input. And once again, that sympathetic input may constrict some vessels, but will also vasodilate others, depending on whether it's epinephrine or norepinephrine as a receptor, so that you will see more blood flow. So it's a pretty big push. If you recall, from the ANS, sympathetic is an action response. And so whether it's, some people call it fight or flight, a lot of people don't like that. A lot of educators don't like that. It's a cliche, but it's something that helps you understand it, that I'm all for it. But it's more of an action thing. You're going to be doing something, you're going to be incorporating your muscles, you're going to be moving your body, that type of thing. Or at least the body needs to prepare itself to do so. So you're going to see an increase of blood flow to the muscle areas. You will see an increase in blood pressure, increased strength of contraction, as well as increased rate. With parasympathetic, you slow the heart down, you will see an increase of blood flow, but it's due to the Starling's law. The more that comes in, the more that will go out. Okay. So that's just kind of a basic short-term regulation there. Another regulation that is a little bit harder to understand is this adrenal medulla. Now, the adrenal medulla has a prominent role in the autonomic nervous system as well as in the endocrine system, so we will talk about this later on in the semester. But the medulla itself is where the catecholamines, or where epinephrine and norepinephrine, are stored. And in the sympathetic nervous system, they have a direct neurotransmitter, an axon that comes right into the adrenal medulla. There's no ganglia, there's no no synapse. So you can see here, we have some sympathetic effects because there's this sympathetic chain ganglia right here. You can see that that's the ganglia right there. Is a nerve cell body outside the CNS where you see a synapse and then it goes forward. This one has none of that. It goes directly to the adrenal medulla. So its effect is very rapid. It's considered short term. It doesn't last very long, but you can see that it will respond independently of other receptors, and it will release epinephrine and norepinephrine, which will then do the same effect as the sympathetic nervous system. And so it's almost like this extra boost of power, so to speak. And it's, once again, a very short-term, very rapid enacting mechanism in order to control blood pressure. And it will help increase that as well. So let's see, we talked about chemoreceptors. Those are mainly, like I said, once again, more sensitive to carbon dioxide levels, high ones. When we have high carbon dioxide in the blood, which we'll learn in very detailed depth, that will give rise to increased hydrogen ions, which decreases the pH. And so your brain is very sensitive to that chemoreceptor. And so anytime we see that occur, we're going to see an increase, we're going to see a response where you see an increase of blood flow to get oxygen to the tissues and specifically the brain. Okay, so then let's talk a little bit about long-term regulation. This is where a lot of students start to get concerned. There's a lot of stuff that we talk about that's related to hormones and how hormones work, and we really don't talk about the endocrine system till near the very end. But one of the long-term regulations of blood pressure is a system that incorporates hormones. It's called the renin-angiotensin system, and our text throws in aldosterone as well, which is another hormone that is influenced by the renin-angiotensin system. So let's go ahead and look at a diagram of that. There it is. And this diagram is a little complicated, but I'm going to try to go over it in a more basic way. So renin. One of the main mistakes students make is that renin is a hormone. It's not. It's actually an enzyme. An enzyme, as you know, is something that is influencing a reaction. Doesn't change the outcome, but can influence it. In other words, it usually speeds it up. So renin is released when we see a decrease in blood pressure. So for some reason in the kidney, this was specifically in the kidney, renin's only in the kidney, and if it's released, maybe the blood pressure is low right at that point where the kidney tubules are, and so it releases renin, like I said, which is an enzyme, and the enzyme goes into the blood and it cleaves, or it changes, it helps break up angiotensinogen to angiotensin 1. So this happens here. You get a couple of these peptides removed and it becomes a little bit more active. And this angiotensinogen is an inactive plasma protein that is there, as, like I said, in the blood waiting as angiotensin 1 goes through the lungs during normal circulation. There's another enzyme here called the converting enzyme, and that takes a couple more peptides off and gets us angiotensin 2, which is a very powerful, very potent vasoconstrictor. As you can see here, it shows the stimulation of vasoconstriction and what happens with that. It also stimulates aldosterone and ADH. It will stimulate an appetite for salt. It will cause thirst mechanisms, which then will also help the secretion of ADH and increases, because of this vasoconstriction, you see a peripheral resistance increase increased venous return to the heart, which increases the blood pressure. Now, like I said, this can look really complicated, but what you need to understand is that this system, it's not like almost like a cascade reaction here. Renin is released due to low blood pressure. That enzyme converts angiotensinogen into angiotensin 1. As angiotensin 1 once again goes through the lungs, it will be, there's another enzyme there that will convert it to angiotensin 2. Strong vasoconstriction stimulates aldosterone, which I'm going to talk about, and ADH. ADH is a hypothalamic hormone that's released in the posterior pituitary, and it increases water absorption. How and why you don't have to worry about till the urinary system, thank goodness. So just know that it helps increase. It's also stimulated by changes in osmolality. But right now you can just know that angiotensin 2 stimulates ADH, which increases water. It also stimulates aldosterone. Aldosterone comes from the adrenal gland, from the cortex, and it also increases water by virtue of increasing sodium, which we'll learn more about once again in the urinary system. So we're saving water. As we save water, then more water is actually stored in the blood, and then our blood pressure starts increasing. So what happens is we lower the amount of urine that's coming out, further preventing the decrease, further preventing the decrease in blood pressure, and actually may increase the blood pressure a little bit. So angiotensin 2 does that. It also has its own strict, very powerful vasoconstriction properties. So it constricts those blood vessels, which causes an increase of blood pressure. And then we also see an increase of water in the large intestines due to the thirst mechanism, which helps us increase volume and increase pressure. So ultimately, this is all due to help us retain water and increase our pressure. And that's how we do it. Water's mainly stored, a good portion of it is stored anyway in the blood, and we see a lot of regulation of water volume, and it ends up being transported in the blood. So we see that corresponding change in blood pressure. Now the opposite is true. If the kidney, at the site of the kidney, if there's a higher blood pressure, the amount of renin decreases, which doesn't give right. So less of this is converted, so less of this is converted, so less of this is released and this is released. And instead of vasoconstriction, we have vessels that are a little bit bigger, so they'll allow for more blood flow, and will ultimately, here what we see is we lose more water, so we can decrease our blood pressure, ultimately, is what we're wanting to do. For your exam, we'll go over some of the depth of questions that you need to understand this, but basically this is our long-term regulation. Once again, it depends on the reference that you look at. Some just call it the renin-angiotensin system. Some will call it the renin-angiotensin-aldosterone mechanism. Aldosterone can also be secreted on its own. It is a hormone, so it has other stimulation to secrete it as well. But this particular, sorry, my arrow dropped on me, series is specifically for mechanism for blood pressure regulation. So it's a like I said, very complicated, but what you want to remember, and maybe I can highlight some of these if I can get the right color in here. Yellow, maybe. So you want, oh no, want this. So you may want, oh no, oh my goodness, sorry. Let's see. You will want to know renin, angiotensinogen, angiotensin 1 and 2. Remember, this happens in the lungs. Ultimately, secretes aldosterone, ADH, and vasoconstriction. That's what that does. And our outcome is increasing blood pressure and preventing further decrease, but we mainly want to increase it if it's low. So that's what you're looking at this big exasperating drawing. Okay, let's get rid of that, shall we? And hang on just for a second. Okay, so that's pretty much a basic recap of pressure and volume and flow. You may see on your quiz or exams this particular, I wanted to share one more with you. Just so you know, you at least need to know what Poiseuille's is. This is really pixelated, and I apologize for that, but that's just how they come down for some reason when I save them. But Laplace's law is another fluid dynamic type of law that helps us with flow, that force is going to be the diameter and the times the pressure. So the larger the diameter, we're going to see a larger force. The smaller the pressure, we're going to see a larger force of, force of flow. And so diameter and pressure are very tightly regulated. Smaller diameter is going to give you more pressure at the same force. And so just know that those have kind of an inverse relationship in the sense that if you're maintaining force, the same force of flow, and you've dilated it, you have an increased diameter, you're going to drop the pressure. Now sometimes we want to dilate, so you're going to have a larger diameter because we want to increase the force of flow, and the pressure stays the same. So this is just, if you see this term, that's where this is coming from. But really, you've been told to learn Laplace's law, so it may try to say, here's an alternate type of thing. So just know that that's what that is. And then the other one I wanted to show you that the other one I wanted to show you before we close was compliance. And this one's also, I'm sorry, very pixelated. I'm going to have to try to redo these. But compliance, in other words, is how well the vessel can expand a little bit. Will have to do with it, the compliance will do with the increase in volume over the increase in pressure. So how well does it handle the volume and the pressure is how compliant the vessel will be. Veins are much more compliant, for example, than arteries because they have more room where they can actually adjust and handle the increase of volume and increase of pressure. So just as another quick thing in case you hear the word or term compliance. Okay, I think that's all. Let me just double check lastly. And if you have any questions after you watch this video, you're welcome to send me an email or to go into the questions and conversations and talk about it there. But I think that's it. So have a great night. We are all done.